Hey, Amelia.
Yeah. Hey, Vijay. So I was looking into the leucine stuff yesterday.
Okay.
I am documenting that notes. I mean, it's available on YouTube. Like, if it's not like something I read, I was just making notes. I'll share it with you guys. Just like
Sounds
that.
good. Okay.
Where is Yeah, if you guys find something interesting, you can add it to that. I didn't add the notes from class. If you have it handy, you can probably add it.
All right, sure. Let me just grab this. So let me do this one more time. Nice.
So
Okay.
it's not a lot, but some notes. Okay.
So you have a Elasticsearch in here, right? The leucine
Right. So
offers.
just wanted to like complete the discussion.
Mhm.
Right. Like if you do it the right way, like how the search engines work. So just yeah, I think autocomplete is a common interview question. So I think we should address both sides of it, like how you design the API and how the storage and how the backend stuff should work. So yeah.
Yeah, here you've got the sort too. I remember this part, merge sort.
Yeah. So I think this is what Ramya was talking about last time, right? So they use inverted index like Google, and then so the additional point is that the so the one of the desirable things about this Elasticsearch is that incremental indexes are fast, meaning that you add something and then you get the index is updated in a very short time, almost concurrent, right? So how that is achieved is by using merge sort. So they have all these indices that already were processed in one big index, and when a new document is added, they do merge sort on the smaller one is merged into the big one. So it's really it's just updated in incremental way. So it's very, that's how it achieves the low latency with the updating. And I think, yeah, and there are like bunch of analyzers. You can write your own analyzer. There are even NLP based analyzers for kind of deriving meaning out of text and kind of indexing that way. So but that's about the actual backend implement, the how exactly the search engine works. The rest is kind of I have some experience with Elasticsearch because we use Elasticsearch. We are customers of Elasticsearch, so I can talk about it briefly. I think we last time we touched upon some key points, right? Like how we should how the autocomplete should work. Like every keystroke should basically be a call. And so the one important thing that was learning from this Elasticsearch, but the leucine thing was that for autocomplete use case, right? You type in V for Vijay. So it needs to pick up. It needs to show results that for all the users that start with V, first name, last name, starting with V, right? So the way it does is by using n-gram tokenization. I think there's a diagram for that. So what is n-gram tokenization is that it maintains index for each character length. So there's an index for all for each letter. So if you type N, there's a separate index that for that key, just one, that character. And then when you type NA, there's another index with the bigram word letters, right? So there's a separate index. So every time you type, you do a keystroke, so it's a different index that it goes to. So that's why the retrieval is super fast. I don't have the diagram for it. I should have a diagram for it actually. I'll put that. It's much more easier to understand, but you get the point, right? So it's not like it's trying to do any algorithm when you actually do this, and it's not trying to filter anything. It's basically the index is already there. It just goes fetches that the results from the unigram index and then bigram index and then like the so on and so forth, right? So it kind of works very well because words don't go beyond like maybe 6 or 7 letters. So max you would have is 7 indices, seven indices of duplicated data, which is, it's kind of Elasticsearch is a very storage intensive application. But so that's the price you pay for the the quick retrievals.
Yeah, great job. This is good information to know about, and just kind of seeing all of this together is really good.
I will complete the notes, but that's the background how Elasticsearch works. Okay.
Mm-hmm. Mm-hmm. I was just going to add that like I picked up 2 courses here. This guy Frank Kane has pretty good course on Elasticsearch 7.
Okay.
And then I found one more here that I just wish listed. So, like every time there's a sale, I try to just kind of like grab a couple more just in the same way like we're talking about stuff. So I have like a chance to kind of go through it and hear about somebody industry standard. Because like this guy worked at Amazon. So I guess he was one of the bar raisers there. So whatever courses he has is really good. So
Frank Kane, is it?
Frank Kane.
Yeah, you can write those things, Udemy course by Frank Kane or something. Yeah.
Should help out with the things we're doing. I'll put this in the Discord, the WhatsApp. All right, so I think this is good. And the exercise stuff that we're doing is great. I see we got more people joining, so that's good. Just real quick, I guess. So how is everybody doing? I just want to get some feedback before we start. Is this group going the way you like? Is it meeting kind of like your criteria for learning? Let's discuss that, and then we can kind of like continue on with what we usually do and make improvements if needed.
Yeah, good to see you, Sadhana. You finally made it. This is the first time you joined, right?
No, I joined in the beginning, and some of the timings are, at least on Wednesdays, it is not kind of suiting. And the last few Fridays, right, we had some long weekends, so it so happened that I was always traveling.
Okay.
I couldn't make it. And it is Friday evenings for us, right? In India.
Yeah.
I was going to say, Sadhana, your voice.
The YouTube videos. Maybe before we start, right, I just wanted to kind of discuss on the last part, whatever was discussed in the last Wednesday meeting, I think.
Hey, Sadhana, it's hard to hear you. Yeah, it's really hard to hear you.
You able to hear me now?
It sounds like you're in a wind tunnel.
Okay. How about it now?
No, like another mic.
Let me disconnect and reconnect again.
Okay. Yeah. We can also send you another mic.
Let me disconnect and reconnect.
Okay. All right. All right. Yeah, it's good to have you, Sadhana. Just kind of like going to the point here. Just, I guess, if you all like the direction we're going, then no problem. We can always, talk about this afterwards too, as well. I think we're doing pretty good. And I think the exercise that we had yesterday or one day ago was pretty good. So just, interested in just hearing feedback afterwards and then knowing like what else you want to get out of this. Okay, so we're almost done with chapter 2. The last time we were on chapter 2, we were looking at a cipher, which was how you would use Neo4j or cipher and like make queries with graphs. Graphs are another way to model your data. So this time around, we're looking at how to make that same query in SQL. And I guess like just to finish this chapter out, because there's not too much left. There are just more some examples here in SQL, like how you could do, searches on graphs for the same information, but you can see that it's just more longer in terms of what you have to write, and you have to be very careful with your SQL syntax. So it's difficult in a relational database. You basically need to know like which joins you need in your query in advance. And then, like in Cypher, within expresses, follow within an edge or 0 or more times. It's very clear. Whereas in SQL, traversal paths in a query can be expressed using something called recursion. So that's why it gets a little bit more difficult. So showing the same query, you can see how the syntax is very clumsy. That's kind of like their point for this page. And then, like reading through all this, yeah, you can definitely see like it's a little hard to follow. So the next part here that I highlighted was that, if the same query can be written in 4 lines in one query language, but requires 29 in another, that just shows that different data models are designed to satisfy different use cases. So it's important to pick a data model that's suitable for your application. So this kind of goes back to that whole paradigm of just, imperative writing versus declarative writing. And then, just also maintainability, because that seems to be a theme, right? So when you're designing something, you want to pick the thing that's maintainable, not like difficult to maintain. There's any questions with that section? Okay. So then we have triple store model and SparkQL. And it would be kind of like nice to learn about SparkQL because I don't have any experience about that. So it'd be kind of fun to look into this as well. In a triple store model, you use different words to describe ideas. So you have subject, predicate, and object. So Jim likes bananas, right? He's the subject. What is he doing? And then what is the object? So Jim likes a banana, right? Predicate is the verb, banana is the object. And so this is equivalent to a vertex in a graph, like a subject, right? So Jim would be a subject. So if we draw a node here, that would be Jim. And then, the edges that he shares could be like, to other vertexes could be like the predicate and the objects. So the object is one of 2 things, as this person is saying. It's a value in a primitive data type, such as a string or a number. So age is 33. So Lucy has properties like age 33, right? Another vertex in the graph. So another edge, another node in that case. So like going back to here, you could have a primitive value type, or you could have another node, right? Like, so one node connected to another node, and that would be the object. So Lucy married to Elaine, right? An object, Lucy and Elaine are both vertices, and the predicate is married to. So I'll just highlight this part here. So here's an example of how you can write these triples, right? So Lucy, a person, Lucy, name Lucy, right? Born in Idaho. So these are your triples. And these would be vertices, edges, vertices, right? So subject, predicate, object. So vertices of the graph are written as this underscore colon some name. And then it only exists because we just don't know which triples refer to the same vertex, right? So So you have like this basic kind of like structure for modeling your data in a graph in SparkQL. And then just basically like, when you start to traverse over this stuff, and maybe I'm not there yet on this page, but this format is called Turtle. I guess, this is a popular format. So let me see here. If you use triple stores, they had like this section here about like the semantic web. The triple store data model is completely different from semantic web, right? And so the semantic web is this idea that websites, publish information as text and pictures for humans to read. So why isn't information also published the same way for computers? So there's a thing called the Resource Description Framework, and that was intended as a mechanism for websites to publish data in consistent format. And so the web is kind of like an internet-wide database of everything, but semantic web was overhyped and so far hasn't really been shown in practice. So, semantic web was kind of cynical. So triples kind of came out of this. So triples can be a good internal data model for applications, even if you have no interest in publishing RDF data on semantic web. So has anybody heard of semantic web and RDF? Just out of curiosity here. Or, do you have anything to add to this section? Just kind of like triples and SparkQL.
Oh, I've never heard of these things.
Okay. It's pretty interesting though. Like I think this is kind of, interesting because like this was sort of a basis for XML in some ways, which was kind of a thing for a while until, people started using JSON. So the turtle language, I guess like that would be like something to highlight in your notes as well, Leo. And then RDF is basically the model for reading, a human readable format for the turtle language, or kind of like this triples structure. And you can see it kind of here, name, type, within. So this kind of like matches up to a graph, right? Vertices and edges. Turtle N3 is preferable as much as it is easier on the eyes. It looks like Apache Jenna. RDF has a few quirks. Let's see here. So it is designed for internet-wide exchange. A predicate might be a URI, such as HTTP, my company space within, or namespace within, lives in, rather than just within or lives in, right? Like generically. So, and this is just, in terms of using XML, you can think that like when you design the data with this model here, the RDF model, you may have conflicts with edges. So you have to like go with deeper name spacing. So one org versus another org within or lives in. So sometimes this data can get a little bit complicated. So then because RDF was a little bit difficult to deal with or to look at in this example here, they moved on to Spark. So Spark is a way to basically like query through this, RDF model here. And so it's, I guess like SparkQL is also like similar to Cypher. Cypher's pattern matching is borrowed from SparkQL. They look quite similar. So here's a query with SparkQL, and it's more concise than Cypher. So here's the prefix, and then here's the query: select a person name, where person, name. These are the triples, I guess, or person's name is person name, person born in within name, United States, lives in within Europe. So basically the structure is pretty similar. RDF doesn't distinguish between properties and edges, but uses predicates for both. And so here you can see like there's another query. This is a Cypher query, and here's a SparkQL query. I guess like the bottom of this, like to wrap up this section, essentially like there's more languages to kind of take a look at, like SparkQL and Cypher, and it would be good to just kind of compare how one way of doing searches versus another adds up. So essentially, SparkQL probably has like simpler syntax, but you may end up with a little bit more. You may have to like sit there and look through RDF or XML a little bit more, like when you're structuring it. Whereas, Cypher kind of works a little bit better with, data that's modeled a different way. So this next section here basically just kind of talks about, are we repeating history? Codicil and the relationship model basically competed to solve the problem of many-to-many relationships. Codicil is kind of like, the original, graph traversal methodology that we discussed at the beginning of this chapter, and then relational is more SQL based. And so here it says that Codicil, a database, had a schema that specified which record type could be nested within another record type. In a graph database, there is no restriction. Any vertex can have an edge to any other vertex. This gives a much greater flexibility for applications to adapt and changing requirements. In Codicil, the only way to reach a particular record is to traverse one of the access paths to it. In a graph database, you can directly refer to a vertex by its unique ID or any index. And then in Codicil, the children of a record were an ordered set, so the database had to maintain that ordering. In a graph, vertices and edges are not ordered. You can sort results when making a query. So, these are just kind of like the main points to just kind of keep in mind when thinking about graphs, like versus like sort of the old way of doing things. Queries were imperative in Codicil and difficult to write, but in a graph, you can write your traversal in a more declarative way, right? As we've seen here in some of these queries so far. Any questions here? Okay, so the last part here, I think, is just this DataLog. And DataLog is an older language than SparkQL or Cypher. It's from the 80s. And basically, DataLog is used for querying large data sets. So Datomic, Cascalog, similar to the triple store model that we just kind of went over. And instead of writing triple as subject, predicate, object, we write it as predicate and then subject object. So this is kind of like something to highlight here. So here's some example DataLog queries. You have a name, and the subject would be, North America. Object is North America, the string. North America continent, USA, the country. So here we're looking for United States within the North American content. Here we're looking for Idaho, the state within USA. Lucy, born in Idaho, right? So these queries kind of read pretty nicely. And so when you have a query, here's a query that's kind of like shown below. It looks different from Cypher and SparkQL, but it's kind of easier to read, right? So within a location, here's the name, here's the via within recursive, migrated, name, born, living in, name, person, right? So these are some rules that they've set up. So born location, within recursive. So recursion just basically kind of means repeating the same steps over and over until like, essentially like finishing like a clause or a rule or business rule and then exiting out. So this thing is going to traverse by recursion until it finds until it completely matches the query. So it says that DataLog defines rules that tell the database about new predicates within recursive and migrated. These predicates aren't triples stored in the database, but they're derived from other data rules. So these complex queries can be built up at a time, right? You can kind of like see that these are getting built up at a time. So for example, name location matches triple name North America with variable bindings location equals North America and name equals North America. A rule applies if the system can match all predicates on the right-hand side of the colon and the dash operator. When the rule applies, it's as though the left-hand side of the colon dash operator was added to the database. So let me see here. So here's kind of like a diagram that kind of goes through this. So within, this is the first rule, right? Within recursive, this database North America with location North America. We're going to go down and apply the second rule. And so you're going to see within North America, within United States, we're going to go to within Idaho, and within Idaho, you can see that within recursive predicate can tell us the locations in North America or any locations contained in our database. Then rule 3, when it's applied, can find people who are born in the same location using the born in filter and live in some location living in. So by querying born in United States and living in Europe and leaving the person as a variable who, we can ask the data log to find out which values appear for the variable who. So it's just this kind of like recursive language.
So question, so in the diagram, right? So the results for the first level Idaho and the second level Idaho, I mean, the vertices are different. Are they called vertices? Yeah, the vertices. So, there is a Idaho in the first level also, right? So how is the, what is the main recursive? So if there are nodes, so like, let's say that as a person who lives in England, but is married to someone who lives in Idaho. So the first level would be England and the second level would be Idaho. Is that how it is?
Yeah, I think, so I think this first starts off by looking at, within the continent, North America. And then I guess, yeah, you're right. It might be kind of looking at, so I think this example here is just seeing that Idaho's in North America using DataLog rules. I didn't see so much about like it connecting the other Europe or who is married to each other in here. I think this is just kind of traversal, like it's showing you the traversal process that DataLog uses to basically go from a location continent down to basically United States, then down to Idaho. And so let's just look at the business rules one more time, right? So here we're saying that instead of writing a triple as a subject, predicate, object, we write it as predicate, subject, object. And so this is how to write the data from our example in DataLog, right? So I'm just trying to like see, yeah, I think this is what they're trying to do. Find Lucy.
No, but that's just the difference in syntax, right? So there is between this DataLog and Cipher, they seem very similar. It's just that the predicate is moved outside. Doesn't really tell us how should we choose one over the other. Kind of. I think DataLog is basically talked about because of its historical value, right? And then okay. So look, yeah, and they both support recursive.
Yeah, let me just pull this here. Datomic queries. It's declarative. It's more logic based. Find, here's a query. These are your rules. These are basics. So find an edge where edge is equal to 42. Oh, well, E. So E, find my variable and then look for an input with tuples with at least 3 components. So here's the tuples with the 3 components, right?
Yeah. So that's.
So I'll share this. I think like it's worth kind of just going through.
Yeah, it's too.
And being familiar with it.
Yeah.
It's a different way of just sort of querying. Here's a video. Wow, nice, wonderful. So I'll put this in the system design section too as well. You know, you can watch this video on DataLog and how it works, like at least the query stuff. I think it's worth just going through it one more time, you know, and just trying to understand, you know, how these queries work. Because as you can tell, it's a little bit different, but I guess, you know, it's another way of querying graphs. So it's, they said it's less convenient for simple one-off queries, but it can cope better if your data is very complex. So here we are, last section. Essentially, we got through chapter 2. I just put some notes again here that, you know, data is huge. We started off by doing a tree, the hierarchical model. So if anybody ever asks you what's the hierarchical model, just think of a tree. But it's not good for representing many-to-many relationships. It's good for more one-to-many relationships. So JSON is a really good way of using the hierarchical model. Then we also have the relational model. The relational model is your traditional SQL. But then as of recent, some applications just don't fit well in relational models either. So now we have NoSQL data stores that are in basically 2 categories: document databases and then graph databases, right? And so document databases, they're good for self-contained documents and relationships, whereas graphs, basically everything is related to everything, right? So all 3 models are used today: document, relational, and graph, and each is good for its own domain. So that's really kind of like the big thing for this chapter, right? Like, you know, there's a lot of stuff to go through, but if you just kind of like take this as like the high level, you know, for moving forward, then I think you have a pretty good foundation.
So Vijay, if we have to put it, I mean, the purpose and the definition is very clear between document DB and relational DB, right? Mm-hmm. But in graph and relational, we still deal with relation. So what would be the major differences? You know, in a simple words, both deals with the relations. Can we consider that relational is not good for complex relations?
Yeah, I mean, you know, like for SQL, I think it kind of came down to, and this might be part of your question, just to make sure, right? Mm-hmm. Yeah. SQL, I think there are challenges with SQL in that it's not as simple to write a query. I think that may have been sort of the pain point for looking into other ways of navigating many-to-many relationships. And that's what the author was really kind of talking about in this chapter, right? Like he spent a good section on like imperative versus declarative writing. And I think that's what it comes down to again, like the maintainability. Karthik, I see you have your hand. Oh, go ahead. Both of you,
so same problem. Yeah, go ahead, Karthik.
So why graph is you would choose graph if you have relationship. Think of an entity relationship within the properties of an entity. For example, if you were to find relationship on the rows of a particular table, so that's let's say any entity, right? So within the same entity, if you want to find relationship between each of those rows of that particular entity, that's when graph shines better. But SQL shines better when you do all the cross relation across tables, right? Many to many. So any data that you have, for example, just users, just a simple example, users in one of the social networking, all the users, if you want to do comparison contrast, then think of it, if it's in a SQL, we'll store everything in a single table. It's not easy to compare, contrast, or query
build relations between the users.
Yeah, within the rows of the same table. That's where graph shines better. Yeah.
I think, to add to Karthik's point, so when you have recursive connections, right, like you want to know friend of a friend. So I think that's where this does better. If it's just like top level rows, like if you just want to persist the relation between rows, you in SQL, you could technically create another, friend.
Yeah, you have to redesign the use case again.
Yeah.
Because it's more of yeah, go ahead.
No, as I was saying, like if you have like n deep relationship, graph, right? Like you have 10 level deep friendship. You want to basically list the entire chain. Then I think graph does better for that particular use case where you are interested in finding if in some way this person is related to that person.
I think from both of you, I got another interesting point is, I think with relational, that rigid structure doesn't expand for different use cases, which were not planned during the design phase. But whereas graph, I think it will provide that kind of flexibility in defining relations between any to any. I mean, we can solve the same problem in relational as well, but it will become more complex and you have to redesign your data model completely.
Right. Right. Also, you can define different kinds of relations also, right? In SQL, you would have to spin up different tables for different kinds of relations. Here, it's kind of you define them on the fly.
Right.
And also the rigidness of SQL, right? The properties of a particular entity, 10 means 10 columns would be there, but in graph, it pretty much supports like this, right?
One other thing to kind of consider with this chapter is that like we had a lot of technology introduced to us. And so it would be good to just familiarize yourself with these technologies over time. Maybe just kind of like look it up on YouTube or wherever, Udemy, SQL, MapReduce, just kind of going through it again, MongoDB, Cypher, SparkQL, and DataLog. And then maybe taking a look at CSS, Excel, and XPath, just to see, like the whole parallels between some of these languages, because a lot of this is sort of built on, those historical ways of modeling data, right? Hierarchical, relational, and then graphs. A lot of stuff is older in some ways. Familiarize yourself again with Codicil, and then see how that kind of came back to what we have today. It says that there are many data models that don't even fit inside of these, right? In some ways, you have to start thinking about how would you model other kinds of data. And that's really what this entire chapter is really about, like modeling data. How would you model data correctly? Some types of examples of stuff that may kind of be outside this is DNA, right? Like modeling DNA, a very long string sequence similarity searches. So searching through a DNA. There's a specialized database software called GenBank, which looks at the genomes. So, if you ever have like an interest in this, you might want to go and take a look at this. Particle physicists have been doing big data for decades using projects like Large Hadron Collider, and that works with hundreds of petabytes, which is super, super huge data. At such scale, custom solutions are required to stop the hardware costs from spiraling out of control. So this is like where your budgets go to for your military. Then also full text search, right? Like this is kind of like something that Google wanted to do for a long time. I'm not really sure how far they got with this, but it's interesting to kind of look at like maybe some of what they have out there in terms of full text search. It's a huge specialist subject. And this is probably like why, like, again, you have to be sort of a PhD at modeling data in order to even be good enough to start to attempt this problem. But this one's pretty interesting to look at. So that's it. We got through chapter 2. Excellent work.
Marathon speaking session for you, Vijay.
Yeah, I was just thinking at times like, oh man, I wish I had some water next to me, but like, it's okay. We're almost done. All right, so actually, before I jump to chapter 3, I would recommend also just going through the references. There's a lot of cool articles in here. I don't know if it's necessary to go through each one, but just kind of like maybe pick a couple and look at them. There's a lot of really top names in here too, like Martin Fowler, Edgar Codd. So it's interesting enough to kind of go and look at who these people are and what they've contributed to the computer science world. Just, the other day, as I was kind of like studying, the other part of this system design, and then there's data structures and algorithms. I was just kind of looking at, who the main person for data structures and algorithms is. And they said it was Joshua Bloch. He's kind of like considered the father of data structures and algorithms. So I thought this was kind of like fun to know. He designed most of the Java collections API. And I guess he was so good that he's like one of the most distinguished people at Google, so he's a big league person. So again, like a lot of the stuff that we use today, like is designed by a lot of these people that you'll see here. So it's good to just kind of go and take a look at who these people are. All right. We're on chapter 3, and this one is called storage and retrieval.
So do you want to go through, I think Akansha put a link in the WhatsApp group, right? Akansha, do you want to summarize like what is that pi theorem? Do you want to speak to it before we kind of move on to other subjects? I put in the chat also. Yeah.
I tried to go through it and I didn't have the clarity that if this is extensively still used and it's valid.
So let's see what I didn't read, but we can probably go through it when here.
This one?
It's a short read, so maybe we can just read now and discuss. Yeah, that
this one, right? Okay. Yeah. All right. So this one's different from the CAP theorem, right? Let's put that side by side. It's another way of selecting a database that is good enough for your system, right? So CAP is consistency, availability, and partition tolerance, but you can't have all 3. You can only have like 2 at most. Whereas pi theorem, this is more about pattern flexibility, efficiency, and infinite scale. And again, it looks like you can only choose 2 out of 3 desirable features in a data system. So here's an example of the pi theorem.
Yeah,
Is anybody familiar with this?
CAP theorem is different, Vijay. We should not confuse. I think we keep running into it. CAP theorem is talking about distributed databases, right? Pi theorem is just choosing any database, like how you could have distributed versions of the same thing.
Okay, so they kind of go hand in hand then together. Is that better? Yeah. Okay, awesome. So is anyone here familiar with pi?
And there's a first. I mean, I didn't even. I think I heard about CAP theorem before, but it was almost, and I forgot about it. So I'm not in touch with the theory side of things.
Okay, so let's read it. It says it's a handy way to think about data needs and choose the right tool for a job. Again, like we can only choose 2 out of 3 desirable features in a data system. Pattern flexibility is all about asking the question, do we want the option to ask new unanticipated questions of our data? For example, we are writing to a movie library and originally modeled our movies to be queried by title. A data with pattern flexibility would allow us to access by genre or author name in the future as the requirements change. So that's pattern flexibility, supports random access pattern and ad hoc queries. Efficiency asks about the performance characteristics of our database. Do we need to serve many distinct queries at the same time with response times of under 100 milliseconds? So performance, if efficiency ought to be one of our 2 choices, we need only a few concurrent queries and tolerate latency of seconds or even hours, then efficiency is not a primary concern. So basically just this block here is just about like latency, low latency. And then infinite scale is how big do we expect the data to grow? More data means more resources, disks, computes, networks. Are we building an application that won't reach millions of users or hundreds of gigabytes of data? So this part here is like how much space you need, right? So flexibility, the ability to change the schema, efficiency, the latency, how fast you get it. And then can this tolerate large amounts of data? And so pi, if you want something with, this pattern flexibility, pick Amazon Redshift or Athena. If you want an IE model, then you should pick Amazon DynamoDB, because DynamoDB can handle scale and efficiency. And then if you want something that has P&E, pattern flexibility and efficiency, but not so great with scale, then you might want RDS or Aurora Serverless or Elasticsearch or Neptune. And then these colors here, red is a relational type database. Green is a wide column type database. So I guess kind of SQL-ish. Pink, document. And then purple is graph. So Neptune's a graph. This is actually good to know. I think this image, we should probably copy it and put it in both of these chats here.
Yeah, it's a good reference. Yeah, it's makes sense.
That way, like you remember, later on, like if somebody asks you something AWS specific, I think the problem with AWS is that like there's so many services, so it's hard to kind of know like what you need. But this kind of helps, like if this last part right here, like if you're looking for a relational type database, then you should use this. If you're looking for a graph, you should use this. If you're using documents, so I like this part of the image. And then I guess, let's see here, let's read this part. So if you want a PE model, pattern flexibility and efficiency, then it's suitable for applications that require fast reads and writes from multiple clients at the same time. So efficiency is a must. Query flexibility is important as applications evolve over time. And then it's possible to use the same database for serving one-line queries and running analytic queries. So relational databases are the most popular in this category. So Oracle, Postgres, MySQL, Microsoft SQL Server. This is when you would use the PE model.
Doesn't flexibility mean that the data model can be modified easily?
Mhm.
No, I think pattern flexibility means your access patterns differ, right? No, it does not mean changing the data model itself, but changing your access patterns. So let's say your major use case
Okay.
when you wrote the code was something, and then you later came up with a different use case. Now your data structure, like your database doesn't support and makes it inefficient. Then it's not flexible with the pattern. No, but like what I have problem with this is it's not intuitive. I mean, I don't think this is a theorem. They just named it theorem. Like ideally for cap theorem, right? You can actually see why only two can be achieved and why, because you are basically compromising the third one for the sake of the two that you choose.
Right.
Here, I'm like, I don't get that intuition.
Sir, also it looks to be something similar. I've just pasted an article. Vijay, can you just open that one?
Sure.
It's like they're talking about why the pi theorem is more relevant than the cap theorem. So probably they're debating against, a better way of choosing. I haven't read the article though, but.
So yeah, I think this would be something that, we want to look into. I think just basically at the high level, right? I think in this age of Amazon, right? And maybe this image was made for AWS. I think it kind of comes down to
right,
more.
Go down, right? They are talking
Mhm.
about how MongoDB fits in this structure as well, or how Cassandra fits in. Come down a bit,
Mhm.
right? They are talking
Okay,
about
sure.
IE systems. It's not only for Amazon related DBs. So somewhere I saw that 1 minute.
Yeah, they were there. I think they are mentioning all other variables. I think they created Amazon, so I think they
Yeah,
tried
the
to put
most common IE
which are
systems
relevant
according
in
to
Amazon.
right. The most common IE systems are MongoDB, Cassandra, HBase, and DynamoDB.
Mhm.
That's what
So
they're
over
saying.
here on this side, yeah, MongoDB, Cassandra, HBase, DynamoDB. So if you need lots of scale and efficiency, I think that's kind of what it comes down to. Like if you're asking these questions, like, oh, I need to be flexible and efficient, or I need something with scale, you can think of the pi theorem as like a simpler way to answer this question, like which kind of database should you go with? Whereas the cap theorem is more about like, consistency, availability, and, partition tolerance, which is more like kind of like a lower level kind of thing for your database, like choosing the right database that can achieve all of these, whereas like if you're thinking like more like bigger, for the user, customer facing, then, the flexibility to change the data, the efficiency to retrieve that data, and then, if you have a high load, then the ability to handle the infinite scale
is what we call partition tolerant.
Did I have a video playing?
So one, to take this further, right? Like for what kind of applications each would make sense, right? Like if you want pattern flexibility and stuff like that. So the pattern flexibility would be a characteristic of data analytics kind of applications, right? So you want to see data according to different dimensions, and so think Athena is a good choice for pattern flexibility requirement. Athena is super inefficient, so I don't know why he calls it efficient, but yeah, but it is too super flexible. So that's there. And then DynamoDB, yeah, DynamoDB. I think that's a given. So it does scale well, and then also offers efficiency. Yeah, I think so. That is where the business, the regular, at least like chat applications, like we use DynamoDB, and so the relational goes to, I think, places where Yeah, actually, why would you want to choose? So basically, if you want to, I mean, I think that was the takeaway from the chapter, right? The document databases have evolved so much that there is no real reason. I mean, there's no real, they're basically catching up with each other's features. So it's basically you get both the features with both NoSQL and SQL databases. But can anybody say where SQL should be the go-to choice?
It just depends. I think like that's the whole point of the chapter, right?
Pattern
like
flexibility is one. Yeah, I think like what they're saying.
It just depends. I think like more interestingly enough, right? Like in moving forward for everybody here, right? Like it's just like, how do you model your data? Like when you're starting, like if you had to start a new project, right? If I were to choose one of you to be a lead, for a project, how would you start off like system designing and modeling the data? Like what kind of representation would you, because based on that is like how everything else gets built, right? Like how we're going to query, a phone book, right? Like, because we were doing that the other day. We had to choose a data model that made sense. So just we went with document, but I think, just kind of tying it all together, right? You have to think about like, okay, what kind of representation are you going to have? How are you going to be able to, query that data? Are you going to do things like graphs where you have to use recursion to go through the graph, or, like, is there some other way of like doing it simply? And then you just kind of look at this, and you also look at this in terms of choosing like a service that can actually do what you need to do to represent, because you have the representation of that model. Now you need to like actually use a service that can work with that type of model and do it in an efficient or a flexible or in a way that scales. So it's kind of like what this part comes down to. These are like implementations.
Yeah. I think SQL is preferred for the pattern. So I think I misspoke earlier. So SQL is a go-to choice if you want pattern flexibility, because it allows joins. So you don't have to keep creating indices. I mean, something is at least possible to query if you come up with a newer access pattern. SQL at least enables you. With the DynamoDB, it's not. You have to create an index, another index, basically copy the table over to kind of make it possible for you to access the data in a different way. So it is a huge overhead. I think, yeah. So if you want pattern flexibility, then yeah, definitely SQL is the choice.
I think SQL is good for most websites, right? Like in general, right? It's when you're using like sites that, do a lot more app-like work, on the front end, like searching or looking for data. Then maybe like SQL isn't as good as NoSQL, like MongoDB, and then if you're thinking about load, like MongoDB does a better job. Whereas like if you're working with big data, right, then you probably want to look at things like, Redshift or HANA, Snowflake, and it may not be necessary to have like a front-facing app, right? Like you may be okay with like queries just kind of like being a little bit, longer to take, but you can be flexible with this data, and you can grow a lot of data. So maybe like a data farm or something.
And just to add on, right, I was just going through the previous video which you all had discussed about this phone book. Of course, I'm not saying MongoDB is DocumentDB was a wrong choice, or a NoSQL was a wrong choice, but I'm just thinking we could have achieved the same thing using SQL as well, right? Of course, we have to agree to the fact that it is a read-heavy system, and we get all the benefits. Like, say, for example, even in SQL, you can go ahead and partition the system. So we can do horizontal partitioning, and we can still go ahead and aggregate the query based on each of the partitions. Say we can have something like, for example, we can have some master slave model or something like that. And in your master, right, you go ahead and allow only write operations. And in your slaves, you go ahead and allow, say, for example, all the read operations. And in master, you kind of map telling, okay, these slaves actually serve from the phone book A to C, or the other slave serves from, serves from D to whatever. So all of these things.
Yeah, I mean, it is possible. Of course, I mean, anything is possible with any of these databases. The problem, the question that we are trying to answer is it the optimum choice, right? So for the phone book use case, basically what you really need is a key value store. Basically, you want to be able to, given a key, you want to look up the document IDs where it is present. It's basically there is no other way of looking at it, right? Like that's the only use case you have. So there is, like coming back to this discussion, there's no pattern flexibility you're looking at. So it's basically for that case, I think key value stores are because they're kind of made for it. You see, there's less complexity. There's no query optimizer, nothing. It's just, you given a key, just give me the document ID. That's all I care, right?
Right.
I mean, you could SQL will over engineer this. That's something that a senior engineer once told me. Don't over engineer problems. So it's kind of it's not needed for this use case.
I'm still not completely convinced. Why do you think? I mean, when you say key value store, right? Which one? I mean, if you can just give a example, kind. So here I mean, at least in the discussion, it was like first name, last name, and then phone number and address.
Yes.
Mm-hmm. Right. So what will be your key and what will be your value?
No, but for the phone book, like we were corrected that basically in a phone book, there is no way for you to go look up based on address, right? Like the index is based on the first name or the last name. That's how the index is ordered.
Correct. So
it's not based on address. So if you want, go ahead.
No, so my point is why, I mean, of course, I'm not talking about the case where I think Vijay brought it up, where we have to go ahead and search as and when the keystrokes are being pressed. So that's a totally different thing. Maybe we'll have to see how exactly we can use try in a persistent way or something like that. But normally given the complete key, for example, what do you say? The first name or a last name, why would SQL not be a correct choice? I'm just trying to play the role of a devil's advocate. I'm just trying to understand why this is not a choice.
I mean, if you use,
what is so glaringly wrong over here?
Yeah, I got you. Right. So the SQL part, right? Like I understand what you're saying. You're just kind of saying, okay, what if I type in a last name, right? And I don't keystroke everything. I just
go ahead and index the first name column and last name column, right? I think Karthik has his hand raised.
Oh, okay, sure. Karthik, do you have something to say? Or did you just kind of forget to unraise the hand?
Yeah, probably.
Okay. I mean, it's simple to write like a query that just says, select star from, database or table, right? That equals where, last name equals this last name, and then have SQL go and run and give you back like the answer, right?
Right. But and you can partition the entire SQL system. And you can still go ahead and you're still not going to go ahead and query the entire thing. Plus, it is not going to be a write-heavy system. So it's like very rarely writes are going to happen. It's like beginning it is going to happen. Plus, the very fact that we will not be having something like, I mean, I don't see a use case where we're going to add some new columns or something like that. So why do we need a pattern flexibility, like adding something new? We're not going to change.
Don't need pattern flexibility, which is why SQL is not a right choice. SQL is a right choice if you need pattern flexibility. So the point I was trying to make is like, I think, like last time Akanksha pointed out, you could still say, like something, if you want just like, let's say the user says Sadhana S, and then you basically execute a SQL query, which says first name like S or something, right? So yeah, I mean, it is completely possible to fetch data using SQL. The entire thing can be implemented with SQL. The question is that the database of choice? Given a choice, you are given a key value store and you are given a SQL. Would you choose SQL over
That's precisely my point as well. Why do I want to choose a NoSQL?
So that's the question I'm trying to answer, right? So okay, so if you, now the question is clear. So you want to be able to fetch results based upon the, let's say, first letter, right? Like that's the n-gram thing that this solution talks about, right? So you so there's an index that basically there's an index that this basically you have a key value database that is maintained for a unigram keys, right? So
no. I'm not talking about the case where we are trying to search for per letter. So that's a totally different thing. I agree. SQL might not be the right one.
Right.
Given the constraint we have removed, given that we have removed the constraint of not searching while the user is typing, for example, and we kind of search only after the user has typed the entire first name or entire last name, why will SQL be not a good choice?
Because here, I'll tell you why, right? Like we'll go back up to a high level, right?
I have a very good point where SQL databases are asset compliant, and we are not looking here for something for like asset compliant, right?
No, like it's more really, right? It's not even a write heavy system. It's like write is going to happen once in a while, or it's already, we can always assume it is already built in kind.
Yeah. So NoSQL databases, there are NoSQL databases which are very good at performing reads, right? You can use there are MySQL flavors which can support that. But if you think you're not looking for something which is asset compliant, which is the basic and core property of a MySQL database, and we are not looking that over here. And that is a very strong point, I believe, for you going over a NoSQL database. I agree you can accomplish this using a SQL flavor, but given two choices, my more weightage would be towards a NoSQL over here.
The reason being we are not looking for the asset property in this particular use case.
Yeah. Give me one use case where you're looking for an asset property here. We are not.
No, I'm not saying we're looking for an asset property. I'm just trying to kind of find a strong reason to rule out something.
Yeah, so I think the SQL is over-engineered for this use case, Sadhana. I mean, there is no, so SQL is rigid in terms of the schema enforcement.
Yeah.
You don't need that here.
I was going to say that was something that we had been not thinking about, or like you can't really do that with SQL. If you look at a phone book, some phone books, right, have, last name and first name fields. Let's see, phone book. But then they have a whole bunch of other things too, so the data isn't always the same per person. Like, let's see here, this person has a PO box, but this person has no address. This person runs a business called Radiant Skincare Studio. So you're just going to have like different fields, in data. So it just kind of becomes a little bit more like if you have a whole bunch of last names, right? And you say, looking for somebody with last name Mehrotra, right? And like 10 people come back with the same last name. How are you going to know, like who you're looking for? You might start saying, well, I remember they had a business. Are you going to make a whole bunch of like SQL calls now to go and look through the businesses as well, join calls? Or are you going to would it be simpler to just have like this data that's already kind of like organized in a hierarchical structure that you can just kind of sort through, in terms of like maybe like seeing it like in an autocomplete, like your stuff comes back up and you're like, oh, okay, this person.
It's like, as you said, if we have somebody with Mehrotra as the last name, we go ahead and query, right? Say, for example, as you said, if we have a different table where we are storing the business column or something like that, where we may have to do a join the next time. Instead of that, if we are doing, say, for example, if we store it in the form of a MongoDB or something like that, where we retrieve the entire document, we have the entire document to make a choice or to query at the application layer, not going back to the DB.
Exactly. Yeah. that's why like again, like it's really important to model the data, like even before you choose like a database solution like MongoDB or like SQL, because it really just like, you know, if you want to take out a whiteboard or something, you know, like it just really comes down to like, how are you going to like look at this data later, right? How are you going to traverse this data? Do you need to make a whole bunch of joins, or can you just kind of have it in a basic tree, right? And I think like sometimes trees are really, really good, you know, like they're just very, very simple in terms of data structure, right? For holding a whole bunch of information. It's only when you need to kind of like get very organized, you know, and prevent duplication, you know, or repetitive stuff from being repeated over and over again. That's when something like structure will help, right? Structured query language. Then you want to move out of like just like a basic tree to like something a little bit more organized where everything's like, you know, managed by foreign keys. And then you have relationships. And then you can like say, okay, this entity is connected to this entity by this relationship or that relationship. And then when that gets to like cumbersome to manage, then you want to start using graphs, right? Vertices and edges, and then kind of use like a more like a simpler, I guess, like, I mean, like graphs are not simpler than structured query, but like, I guess it's just like a little bit more flexible, you know, in terms of managing many, many relationships. So this stuff like the MongoDB or SQL, right? Like that should come after you've actually like thought about like how the data should be represented, like in your own head, right? Or on a whiteboard or on a piece of paper. And then you pick like the best like business solution that will help you achieve that goal.
Right. I mean, I was just trying to, I just went through the video and I just wanted to bring this up so that.
Yeah, if the question is it feasible? Then yeah, I think it is feasible to use SQL, no problem there.
You know, I was just, I mean, of course, we can always argue all the use cases you can somehow fit in either of the models kind. But if there is a strong reason why we can rule out one thing, right, then it makes our lives easier.
Definitely.
Yeah. The reason for me would be I don't want to so for a simple use case like this one, I do not want to use these SQL adapters, and like I have only one use case, right? I just want to just given a key, just give me back the results. I do not want to complicate. I mean, the reason, so any enforcement comes with an overhead, right? Which adds to the latency, right? I'm sure the optimizer does this checks and all, which is, so that again goes back to the imperative versus declarative kind of usage, where every operation, basically the query optimizer kind of, you tell me what you need, and then I'll basically make sure that it is queried the right way, and then I will decide how to query for you. Here it's so simple that I can actually optimize it myself, and I don't need to take the overhead of something else doing whatever custom made like whatever specialized logic it is trying to do.
Right.
Okay, I gotta say it's 8:45.
Yep.
So we're 15 minutes over. But that's a great discussion. And we're in really good shape. I think we got a lot of value out of this particular study group today. And I do like how we kind of sometimes go away from just reading the book to just kind of talking more about like, all these different theorems and like asking the questions of why you'd pick, because it's ultimately like, you're probably going to have to know this at some point in the future. So it's good to just hash out like, what are these things and why you even need them? Because textbooks sometimes can be kind of dry, but now like everybody here has like a really good understanding, I think, of why you pick one over another. So feel free to just keep looking through, videos and the stuff that we talked about, the articles, the Discord, and then the WhatsApp and all that. So I'll see you all next week, Wednesday, and we'll start chapter 3.
Chapter 3, or do you want to take another design question?
Either way. What do you all think? You can leave comments or feedback, in the chats too.
I think we should do chapter 3. I mean, as we gain more and more knowledge reading this book, our system design will improve more and more. So
yeah,
after every chapter, we can do a system design.
I'm good with that.
Yep.
Or even halfway. if you want.
Yeah.
Any conclusive remarks on using SQL versus NoSQL?
Again, just pick one, based on your needs. Like if you're going with something kind of more hierarchical, then go with.
I think
JSON.
one key point that's missing here is just not the needs. It's the team's from a maintainability perspective, and also team's familiarity with the technology, right?
Got it. Yeah.
And also from a hiring perspective, tomorrow, if you want to add, so a lot of factors come into play choosing that within a team environment, right? That's something that I think we haven't factored in, but just wanted to play in before we start.
Yeah, that's true. Like just the comfort level of the people that work with you on the project. I think we live in an age now where, being a software engineer is kind of like extremely difficult because like they have to know like hundreds of different things, right? So,
Yeah. I routinely get thrown under the bus to take up something completely new, like I don't know anything, and basically with a hard deadline. So yeah, that's just the reality of life. When Karthik said, the familiarity, there's no such thing. You are just given something and put in a sprint and you're supposed to deliver that. That's all there is.
Yeah, it's hard. It's very difficult. I think,
Yeah,
just
so
constant
familiarity
learning.
is someone has to dig in the new, right? Constantly fun, in my opinion.
You broke up a little bit, but I think we're catching. Karthik, you're breaking up. But I think I got your point.
Yeah.
Right. Yeah. So.
Okay. So next chapter.
Right. Yeah. So we'll start on this next chapter, and then we'll throw in a design question as we get there. So yeah, thank you all for coming, and I'll see you next week.
Yeah, feel free to update the Notion link with like whatever your insights out of the session, or like if you have any experience and stuff. Okay.
Will do.
Yeah, and Vijay, you were just projecting one more article, right? That in that Notion, that designing a phone book or Elasticsearch. I mean, it's in the same notes as us as we are maintaining, or it's somewhere else. You could just paste this, right?
Yeah.
This is one other link, I think. Let's start looking at the Notion and all the notes we've got so far, and then maybe try to like organize it together.
I don't think you can kind of put it in a folder. I'll see if I can do that.
So I'll show you like how I do my Notion, and then I have to really jump for real. So I'll just do this real quick. But so for example, right, I have like, if I'm studying data structures and algorithms, I'll just start off by making the main, and then I'll have links to important parts of this topic. So DSA, I'll say here, time complexity, essential data structures.
Okay. Got it.
And then, algorithms. And if it becomes very complex, then like I'll make a new page, like for example, Java collections. If I need to go and take a look at this, I'll see it here. But yeah, I would try to like organize it in this fashion where it's kind of like hierarchical again, right? Modeling data. So that way, like we can easily retrieve this data and understand.
Right. Okay. Then I'll just basically remove that new link and then put it in the same thing as the original link I had shared. Okay.
Good stuff. All right. Go model some data, everybody. Talk to you next week. All right.
Bye.
Bye. Bye.